Hi, I'm Irfan, and I'm a PhD student at the Biomedical Signals and Systems Group at the University of Twente in the Netherlands. I'm going to start my presentation now. There. Today, I'm going to talk about instantaneous center of mass velocity using a minimal IMU setup. I would like to thank the organizers of IEEE Sensors and the focus session for allowing me to present my work here. Thank you. Today, we will talk about gait biomechanics and how I plan to use inertial measurement units as wearable alternatives, looking specifically at the question of extracting 3D instantaneous center of mass velocity. I will show you the experimental protocol that I used to test this method on healthy subjects and also my findings and takeaways. Gait biomechanics is simply the measurement of the kinetics or kinematics of gait. In order to understand gait patterns, we may use it to understand healthy walking or just normal gait patterns, or look at gait impairment and see how we can improve that, or simply understand sports biomechanics, trying to improve the performance of an athlete. We can measure the spatiotemporal measures, which includes the step length, step width, and so on, or we look at balance measures. One such example is the extrapolated center of mass, where we look at the movement of the center of mass within the base of support and try to understand whether the person is stable or not. What we find is that there are several measures of gait which require the knowledge of movement of the center of mass itself, and therefore measuring that is quite useful and important. In order to measure the center of mass in an accurate or using the gold standard method is to apply optical markers on the body and try to see as they move how the center of mass of each segment moves, and from that derive the center of mass of the complete body. We may also use force plates or treadmills that measure the forces while walking, the kinetics, and thereby we can estimate this movement of the center of mass. These systems, as you might imagine, are either quite intensive for setup or have a restricted measurement area. You can't go out and measure someone who's doing sports or walking out in the wild. And that's why we need to move towards wearable systems. There are several of these systems, which includes pressure sensors and so on, pressure insoles that is. But here we focus on inertial measurement units. These small devices measure the accelerations and angular velocities of the segment or the body part that they are attached to. They're really portable, they can be small, and they theoretically have an unlimited measurement space. You can go out and measure them in the wild, and they don't restrict you from being free in your movement. But the main issue that everyone has to deal with when talking about IMUs is drift. And that is solved by using strap-down inertial navigation. The idea of drift is that when we want to estimate velocities or positions from accelerometer signal, first we have to correct for gravity, and after we have them in the frame of the person walking, we have to apply integration. And now this integration introduces errors into the estimate of velocity. And we try to fix that by applying some idea about the initial and final velocity, some sense of these values. As you can see in the graph, the blue is the value of velocity, which we get from integrating accelerations, and the red is the corrected, the drift-free version of the velocities. And we were able to get this because we had an idea of the initial and the final state of the velocities, which here we assume to be zero. Therefore, the question that I'm going to ask here today is a minimal IMU setup sufficient, given that all that we've seen so far, for estimating instantaneous 3D center of mass velocity for overground gait using physical principles? I say physical principles because extracting center of mass velocity has been shown in literature, but by using machine learning methods. And this includes the work of Zhang and Sabatini, and they require the need for measuring or collecting data sets, training data sets to improve their model. We could start with the stable inertial navigation and see how far we can get, where we look at the pelvis accelerations, as you can see here, transform them to the CS frame, which is similar to the body frame. So it keeps track of how you're moving. After removing gravity, we apply integration to get our STI, velocity center of mass. The problem here, as you might imagine, is that there is no quiet period during gait. The person is always moving, and when the measurement takes a long period of time, we are unable to reduce the drift that creeps in the end. We cannot apply these special tricks such as zero velocity updates because we don't know any information about the movement of the velocity or the change in velocity over time. What we can do to remove drift is apply a high pass filter. And the high pass filter makes sure that the drift is removed, but the problem there is that it leaves out all the low frequency information. So we have, in the end, an idea of the instantaneous change in the center of mass velocity, but no idea about how the average velocity of the person itself is, in which direction is he moving and how is he walking and so on. In order to compensate for that missing information, we try to see, are there other sources on the body that we can get an average velocity of the body from? And for that, we looked at the foot velocities. Foot velocities are more reliable if we use an IMU setup because when the foot is moving, we have specific instances of contact where the foot's velocity can be assumed to be close to zero. We make that assumption, we can reduce the drift in velocity for the feet. We can do that for the right foot and the left foot. And when we average that and apply a low pass filter, we found that we can get an idea of the average movement of the body in all the three directions, the X, Y, and Z, which is the forward, medial lateral, and vertical directions. So we want to test this out by checking if fusing these two sources of information, by fusing the high frequency information and the low frequency information, we have two sources, we get the best of two worlds, and we get a really good estimate. We want to test this out by, of course, doing an experiment where we had 6 subjects, all of them provided consent. We asked them to wear an IMU at the pelvis and on each foot. We also placed VICON markers on their hip, and this was our gold standard in order to measure how the center of mass velocity was moving when they performed the different tasks. They performed each of these tasks 4 times. It included straight walking and at the preferred walking speed, performing the same task with a right turn, straight walking plus a 180-degree turn, straight walking plus 2 of these 180-degree turns. So here the measurement duration is longer and there's more variation, and also a zigzag walking, and also a simulated asymmetrical gait in order to simulate impairment in the gait and see if this method works in that case. What I'm showing here are the results, are our findings for one particular subject who performed the walk and turn twice test. What they did was they started walking, and on this instance, they kept walking forward, made a 180-degree turn indicated by these red bands, kept walking, made another turn, kept walking, and overall covered about 15 meters or so. The data that you see here, the top subplot is the anterior-posterior direction, then we have the medial lateral, and we have the vertical direction. In blue, we have the instantaneous change in velocity, which we got from the pelvis accelerations, and in red, we get the average movement of the body, which we got from the foot velocities. We did that for, as you can see, we can get that for all the 3 axes, and when we fuse them, we get an idea of the movement of the center of mass velocity itself, which here is shown in blue. In red, we have the reference velocity of center of mass, which we get from the VICON markers placed on the pelvis, and we compare them for all the 3 axes, the anterior posterior, the medial lateral, and also the vertical direction. What we do find is that there is good correlation in all the phases of gait, the initiation of gait, the walking, so all the cycles involved, the turning, there are 2 different turns, and also at termination after several seconds, after 20 seconds. We see that it's nicely estimated in the all the 3 axes. There are some deviations, but overall good correlation with the reference. What are implications and takeaways? Well, we tested this method for all the different kinds of walking tasks, so wearable gait over ground, and we found an average of 10 plus or minus 2 centimeters per second error across all axes. And we found that this was actually close to or better than what Sabatini found using their approach. Therefore, an IMU-only approach can give you an instantaneous estimate of 3D velocity of center of mass, and we were able to do that during gait initiation as well as during termination. And you can see that we don't need any training or modeling steps, just using simple stable inertial navigation and physical principles. Of course, there are some limitations which require the need for a special calibration method, which is explained more detailed in the paper. And we also assume that the center of mass moves through the pelvis, and this has to be taken with a grain of salt, especially when the person has more asymmetrical walking or asymmetrical posture. What are next steps? What we plan to do is to estimate center of mass position and how that moves using this improved estimate of center of mass velocity. We are also using a theory called the centroidal moment pivot, where we try to find the relation between movement of the foot and center of mass. You can see our published papers, and it really improves the estimate of the feet and center of mass using simply a 3 IMU approach. Our next steps is to look at balance measures, see how reliable they are, and also test these algorithms on patient data. I'd like to conclude by saying thanks to all the partners involved in the Ambition project, and which is mainly funded by the Dutch government and WO. And we have really nice academic partners, including Amsterdam, Erasmus, Roessingh, also several companies, as you can see here, all across the Netherlands. Really good initiative and really good results and discussions. And that's it from me. I would like to thank you for listening to my talk. And please feel free to ask questions, and I wish you good luck with the rest of the conference. Thank you and bye-bye.